Okay, continuing part 2 of inference for regression. The first thing we're going to do is a regression slope t-test. But before we jump into the mechanics, I just want to briefly talk about what the idea is. Okay, here's a picture of our sample. These are the 12 data points we've got from this particular sample of all these babies. And this is, remember, this variable is the temperature at 6 months, and this is the age at first crawling. And it's not true that these data points all fit on a straight line, obviously. But we can fit a straight line and say the best possible straight line, in the sense of least squares, is this straight line here. And that's the best possible prediction of if you give me a new baby and say, okay, I know the temperature is going to be 40 degrees and when they're 6 months old, what's your prediction for when they're going to first crawl? Okay, so we've got one level of fiction and modeling based on the fact that these aren't really on a straight line, even for the sample, and then we're fitting a straight line to it. But there's another level now with inference and sampling that we've got of fiction here, and that's that if we did another sample, the dots would look different. I made them so that they weren't incredibly different, but they're different data points, and it would have a different regression line. If you put them all together, you can see a little bit better. Here's the original regression line, here's the new regression line. They're not quite the same. If you look at these different samples, you're not going to get the same kind of prediction. And of course, what we'd really like, it's not really that we care about samples, it's we really want to look at, say, the whole population. So here's, I imagined that there's only, maybe a few hundred babies in the United States, and here's every baby plotted. You want to imagine this is really millions of data points. And there's some sort of magical regression line. Again, it's not really the real reality even for the whole population because they're not on a straight line. But it's the best straight line we could possibly get if we have access to a census of every single baby. That's kind of the ideal what we want to get, the true population regression. I even used my red pen because I love using the red pen. Let's see. What do I want to do? Got this weird blank space. Imagine that there's just many data points, and we look at the true straight line. Okay. The point is that the straight line that we've got from our only data that we have access to, right up here, is not really the real thing. It's going to have a little bit of a different slope and intercept from the magic real thing that we have down here. Okay. But we don't have access to that. So that's what we're doing here. So let's look at the mechanics. We go to stat tests almost at the very bottom, F. That's the Lin Reg T-Test. And here's, when you press that, here's what you get. We're going to put in L1 and L2 for our X list and our Y list. We don't have a frequency list in this example. I chose to do a two-sided test. It would be pretty defensible to look at a less than 0 because we could specifically test the hypothesis, is there a negative slope? But I just went ahead and said, is the slope different from 0 at all? Now hopefully, unless we're really misleading ourselves, when we look at this picture, let's go back up. When we look at this picture here, it really does look like it's negative. Now, but that might just be sample variability, and the t-test might tell us, with such a small sample, we can't really be sure. And that's what we really need to know from the t-test. Okay, so here we are. I went ahead and put in Y1 for the reg ec, and as I was saying in the previous video, even if we hadn't done the regression analysis before, this is going to tell us all that right here. And so the more efficient way to do it is kind of skip right to here. Okay, and we'll do that once we get a hang of it. Okay, so here's the output you get. It's 2 pages almost of output. Y equals A plus BX, that's what they use instead of B naught and B1. Okay. The regression, or the inference is the slope, the true slope, beta, which is the true version of B, is that not equal to 0? And the t is a pretty big t value, pretty big negative, and the p value is 0.0008, something like that, 8 times 10 to the minus 4. That's very small. So yes, we can reject the null hypothesis. It does look like there's a real association here. That this is predicting that if all those assumptions and conditions that we sort of checked and are sort of true, if those really are true, if it's all randomized and independent and representative, then it's incredibly unlikely that the observed downward slope that we're seeing, keep going back to here, in our sample right here, it's very unlikely that that downward slope we're seeing is just due to random chance. And we probably would see it if we had access to the real population. Okay, and then it gives us the A and B, which we got before from the standard regression. It gives us the S, that's the standard error. Okay, and then the R squared again. Okay, so the one thing it doesn't give us, this is the standard error of the residuals. It doesn't give us the standard error in the B quantity, and they talk about in the book how that's a really good thing to know. That's just a natural ruler of, given this sample, how much variation are you likely to see in the slope. So roughly it's sort of saying, if I took another sample, how much would I expect the slope to change by? They point out that even though the calculator isn't quite smart enough to give that to us, you can take the B value here divided by the T value, and you can get that. You can reverse engineer it. So this says that the slope we got was a minus 0.08, and the standard error in that slope is that's right. I forgot a 0 here. It's like, that doesn't make sense. There we go. Is about 0.0167. And so that's a pretty small variability compared to the B we actually got. That's another way to say that this is probably meaningful. It's probably meaningfully different from 0. We got a slope that looks different from 0, and it's probably not random because of the comparison with the standard error, or in other words, because of the T value. Okay, so the conclusion is that we do see, well, we reject the null hypothesis, which was that there was no association, or no, let's say no linear association between temperature and crawling age. Okay, there really does seem to be a meaningful association. There seems to be a meaningful association in the whole population. We're quite sure that in this sample there was an association. That's really quite clear between these variables. But the more interesting thing, where inference is coming in, is that we are extending that to a claim about all babies. Okay, so in the next part, I'll go ahead and do I'll do it. It's pretty quick. Let's just do the 95% confidence interval for the slope. Okay, so we can get a little bit more precise about that by saying, okay, we love to have this slope of the ideal regression line. We're never going to get it. That's beta 1. We do have B1, or what the calculator just calls B. And we'd like to get an idea of, with this B value, at the minus 0.078, could we put a plus or minus on that? We think that you get about 0.08 weeks per degree. 0.08 plus or minus what? What's a good confidence interval? Okay, so that's stat tests G. It's right under F. It's Lin Reg T-Int. You put in xlist L1, ylist L2, frequency 1. Again, this is going to depend on exactly how you're doing it. That's what I'm going to do. For 95% confidence interval, obviously you put in 0.95 for that. I put in the regx Y1 in case we didn't already have it. It's already loaded into Y1, so that's not too important now. And we get a lot of the same data. We still get the B, we get the A, get the R squared, a lot of the same kind of data. But the key thing is right here at the top, near the top, and that is the confidence interval. So the conclusion is we are 95% confident that the true slope of the ideal linear regression line, that would be for the whole population, if we actually could get that, which we can't, and it is some fixed number, we're not saying it's random, it's some fixed number, we're 95% confident that we've captured that, is captured in the interval from minus 0.1153 to minus 0.0407. And notice that that interval doesn't even come close to including 0, which is another confirmation that we don't believe the null hypothesis, that there's no association here. We think there's a negative association, and if you want to say how much bang for your buck does 1 degree get you in terms of earlier crawling, we think it's between minus 0.04 per degree and minus 0.11 or 1.15 per degree. Alrighty.